Well, hello everyone, and welcome to week 10 this week, Paleoclimate part 2. Notice part 2 here, number 2. We discuss the material that follows the oxygen 16, oxygen 18 discussion of last week. Please remember that the material discussed last week at the end of last week's video will merge with this material and form the basis for week 10's homework and week 10's quiz. There is no forum this week. And that's so that you may focus on this paleoclimate material. Okay? So having said that and putting that into context, let's get going. Again, paleoclimate. We're going to talk about now orbital variations and ice ages. Why do ice ages happen? The variation in timing and intensity of sunlight. First, we have to realize that the Earth is a tilted sphere at 23.5 degrees to the ecliptic. And the ecliptic is the plane that the solar system really makes with all the planets and the sun. So basically, in that sense, if you talk about the sun, if you draw like a sheet of paper right through the middle of the sun, that plane, P-L-A-N-E, would go right through the middle of the Earth, the tilted Earth at 23.5 degrees. So that's what's called the ecliptic. Of course, because we have a tilted Earth, we have seasons. So we are basically past spring, headed into summer, eventually fall and winter. In summer, the northern hemisphere is tilted toward the sun, and in the summer, the southern hemisphere is tilted toward the sun. Now, during our summer, or the southern hemisphere winter, they are tilted away from the sun, which is what happens to us in December. So basically, that's the reason for the for the seasons. Paleoclimate deals with insolation. Remember, that's an acronym for incoming solar radiation, and we really care about the amount of energy that any point on Earth receives during the year, measured in watts per meter squared at the top of the atmosphere. So orbital variations come at regular intervals known as Milankovitch cycles. And this is significant because humans have no impact on this, although humans would be affected by it. So Milutin Milankovitch was a Serbian mathematician, and he calculated these cycles, brilliant man, and he realized several things. So there are 3 parameters. The first is the eccentricity of the Earth orbit about the sun. So the orbit of the Earth is either a circle or an ellipse. Right now it is mostly circular, but oftentimes it changes in shape to a more egg-like shape. And that has to do with the impact of other planets like Jupiter and Saturn on the Earth. So basically, those 2 big planets have an influence of nudging the Earth into a slightly different shaped orbit. And as a result, you sometimes have an orbit that is more egg-like versus circular. Okay? So that is called the eccentricity. This changes on a scale of once every 100,000 years. Now, the next one is obliquity, and that is the tilt of the Earth. So the tilt of the Earth is about 23.5 degrees right now, but it can vary every 41,000 years between 22 and 24.5. And that makes a difference on basically how the seasons progress, okay? And the last one is called precession, and precession is the direction of the Earth that the Earth axis points to. Right now it points towards Polaris, known as the North Star, but oftentimes that begins to sort of wobble. And the only way I can think of explaining it would be what happens when you spin a top And eventually that top is nice and tight, but eventually begins to sort of lose its energy and it begins to wobble. And that wobble is called precession. So these are the three orbital parameters that we will deal with. So there it is, eccentricity, circular versus elliptical. Obliquity, the change in the angle that the Earth axis is tilted every 41,000 years. And then the wobble or the precession, making seasons much more difficult to predict. Okay, so now let's look at paleoclimate from the perspective of these orbital shifts. There's the sun, beautiful graphic, isn't it? So imagine the orbit. The orbit can be mostly circular, which is what it is right now, but we're still not perfectly circular. So we're closer to the sun in January, called perihelion, and farther from the sun in July, that's called aphelion. Okay, and this is obviously exaggerated just to give you a sense of where things are. So basically aphelion farther from the sun in July, and perihelion closer to the sun in January. Okay? This right here is meant to show you or highlight the tilt of the Earth. So in January, we, the Northern Hemisphere, are tilted away from the sun. That's our winter. And in summer, we're pointed toward the sun. That is our summer. Now, let's look at the idea of eccentricity effects. So the eccentricity shifts seasonal contrast in the Northern and Southern Hemisphere. So this is the reason why it can have an impact on climate on a long-term scale. So high eccentricity, that means it is more egg-like, like a big ellipse. Okay, so in this case, the Northern Hemisphere, notice, is pointed toward the sun and closer to it. So it would have hot summer, and then the Northern Hemisphere would be tilted away from the sun and really far, cold winters. Conversely, the Southern Hemisphere would have moderate summer because it is pointed towards the sun but far away, and tilted away from the sun but closer. Does that make sense? So if you need to sort of stop the presentation and look at it for a few seconds, please do that. Again, in this case, the Northern Hemisphere would have a hot summer and a cold winter. Winter because it is tilted away from the sun but far, tilted towards the sun but close. So the seasons would be exaggerated, much more severe in the Northern Hemisphere. In the Southern Hemisphere, the effect would be basically the opposite. It would be much more moderated as a result of this particular configuration. Now, here is a more circular or low eccentricity orbit. So in this case, seasonal contrast would be the same in both hemispheres. And that's roughly where we are now in the year 2020, okay? So now let's look at obliquity. So the idea of the angle of the Earth axis. Notice how this is much more exaggerated than this. Can you see that? If you can't, stop, take a look at it, let it sink in. So this is changes in sunlight at high latitudes with little change at low latitudes. So let's look at this for a second. In this particular case, the Northern Hemisphere would be high tilt, hot summer, or hotter summer. In this case, low tilt, cooler summer. And it would be cooler summer because it's almost like having a light pointed directly at you or having a light at an angle to you. The intensity of it would be much more significant or much less significant depending on the scenario. Here's the idea of precession. Now precession would be the wobble. So at this point, you're pointed toward, but now you point it away from. So it's much more difficult to predict the seasons. Okay? So the seasons become less predictable due to the tilt changes. In this particular configuration, the northern hemisphere would have a hot summer, and the northern hemisphere would have a cold winter. Can you see that? Northern hemisphere tilted away, but far, tilted toward, but close. Southern hemisphere would be mild. That would be like the example we showed earlier. Now, in this second example, the northern hemisphere would be mild summer, mild winter, because you're tilted toward, but far, tilted away, but close. Now, in this instance, now it's the southern hemisphere that would have a colder winter and a hotter summer. Can you see? Again, it's worth stopping it for a few seconds, taking a look at it, look at the graphic itself. I know it's not the highest quality graphic you have ever seen, but I exaggerated the shape and the tilt just to give you a good chance to let it sink in, okay? So today, perihelion happens in January, aphelion in July. So the northern hemisphere winter is warmer than the southern hemisphere winter, and the southern hemisphere summer is cooler than the northern hemisphere summer. That's Earth today. Now, the combined effects of obliquity and precession lead to a significant change in solar radiation at higher latitudes. So basically, short, cool summers in the northern hemisphere leads to snow lasting through summer, ice sheets grow. There's an ice age for you, okay? Now, positive feedbacks, remember that? Remember that term? Remember that whole idea? So think about it. There is a circle, temperatures cool, ice grows, reflect more snow, temperatures cool more ice grows, more reflection of sunlight, temperatures cool, which leads to the growth of ice. Get it? It becomes a self-sustaining, reinforcing feedback. Again, don't confuse positive with good and negative with bad. Positive is reinforcing, but negative is counteracting. That's how you need to remember what a positive and negative feedback happen to be. Now, let's look at this example. On the top one, ice. On the bottom one, no ice. This one is a no ice example because the tilt is it's less. So the sunlight is never extreme or as extreme. So therefore, winter snows last through summer and ice sheets will grow. In this example, no ice because it is a much more tilted Earth, meaning the summer is hot enough to melt the snow that fell during winter. So every fall and winter, the next year, you have to sort of start from scratch, okay? So 20,000 years ago, we had high eccentricity, we had low tilt, and the northern hemisphere at aphelion was farther from the sun. And that is basically when New York State was covered by glaciers. What we referred to as the Catskills and the Adirondacks in New England was basically under about 1 kilometer or more of ice. Okay, that's the New York State of a long time ago, which if you've ever done any hiking, you know that New York State is a glaciated landscape. Westchester County, Putnam, Orange, the Catskills, okay? Now, here's an example during a circular with no glaciation. In this case, notice great tilt. So summers are hot. So the ice and the snow melt in summer. In this case, notice the slight tilt. So therefore, summers tend to be cooler. Right now, the eccentricity is too low. The tilt is too high. And the northern hemisphere is at aphelion, so it's farther from the sun. So this is a reason why we're not in a glaciated time. If you take away humans and fossil fuels and all that stuff, if you simply look at what we have in terms of orbital parameters in 2020, okay? Now, so basically major glacials and interglacials every 100,000 years. And then there's this thing called stadials and interstadials every 41, 23, and 19,000 years. Okay, so a glacial is, of course, an ice age. An interglacial is a period between ice ages. That's where we are now. A stadial is a warmer period, and an interstadial. So these are like minor events that happen at smaller time intervals. Notice 41, 23, and 19,000 years. These are all due to these orbital parameters. So now if you look at it from a graphical standpoint, here you have eccentricity every 100,000 years, obliquity every 41, and precession every 23. So when all the peaks line up, you tend to have a period of warm, notice warm, 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 versus periods of cold, 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 cold. So when they do line up together, you get a sense of ice ages coming into effect, versus when they're not, like they are right now, when they're not in sync, then periods tend to be warmer, okay? So this is talking about the idea of Antarctic temperatures. This is talking about tropical temperatures. This is talking about sea level. So whether sea level rises or drops, depending, of course, whether you are in an ice age, which usually means sea level is low, versus a warm period when sea level is high, okay? Now, total forcing or insulation to glacial interglacial cycles is often recorded in marine sediments, and the timing and magnitude don't match. So this is the idea of basically talking about insulation is not the only driver of climate change. In this case, humans have begun to have a significant role in it, okay? So, you know, Earth surface environments change, vegetation patterns, ocean currents, of course, mountain ranges are formed. And whenever you form new land, new rock, you take carbon out of the air and turn it into part of the stone. And that becomes a drawdown of carbon dioxide. So the Earth tends to cool, okay? So you have to consider all kinds of feedbacks that are sort of coming into play. Not just, of course, the drivers due to solar and orbital parameters that we just discussed. Computer modeling of paleoclimate, you cannot reproduce the past climate changes with orbital forcing alone. So you also have to consider changes in CO2. Past climate changes initiated by orbital changes were also enhanced by basically greenhouse gases, which is what we're doing now, but we're doing it artificially. Okay. Past warming led to CO2 rises, and today CO2 rises is causing warming. So again, this right here, this line, is the idea that humans are the ones leading to a significant change in the makeup of the atmosphere, and that makeup of the atmosphere change is leading to a bump up. Remember, we're making that blanket thicker, okay? These are the idea of positive feedbacks. So again, orbital forcing, smaller temperature increases in CO2, the amplification of temperatures, and the idea of ending glaciers around the Earth, whether they be mountain glaciers or whether they be ice sheets, like what you have in Greenland and Antarctica, okay? Rapid climate change. So this is leading back, this is about the period from 12,800 years ago to about 11,500 years ago. It's called the Younger Dryas. It is a cool episode which interrupted this post-glacial warming that had been happening for a while. Conditions lasted for a little bit over a millennium, and then it went right back to warming again. And the Younger Dryas ended up with being about 10 degrees warmer in about a few decades, which is kind of significant. That's enough to melt a significant portion of Greenland, which of course would raise sea levels by several meters. And here's the idea. So this is 8,000 years ago, 10,000 years ago, 12,000 years ago, all the way to 22. So this is when glaciers were thick throughout most of North America, Canada, the US. Then we began to come out of the ice age. We began to warm up. And then there was this rapid period of cooling again, followed by warming. And this is where we've been all throughout, really the past 10 to 15,000 years, 10 to 11,000 years or so, okay? So that's the beginning. So most people think of the end of the Ice Age at about 11,000 years or so ago. Since that point, we have been decidedly warmer on a global scale without much change. The conveyor belt hypothesis. So this right here is saying the following. The global ocean conveyor belt is in the North Atlantic. The Gulf Stream flows all kinds of warm water towards Europe. That water cools, becomes salty, and then sinks. And then it creates, remember that thermohaline circulation? Remember that term? Well, the idea here is what happens if you get a negative feedback going, meaning you warm the globe, you melt Greenland, which means you dump fresh water into the Atlantic. You basically make the water fresher, which means less salty, less heavy, and you interrupt that three-dimensional thermohaline circulation. So in this case, warming led to cooling in the North Atlantic, and Europe would experience glaciation. That's a negative feedback. And it's negative because warming led to cooling. In a positive feedback, if you recall, warming would lead to more warming. Got it? All right. So here's the idea. What about today? Milankovitch cycles predict that we should be cooling. Okay, but that's of course that's not what is happening. So in today's warming, simply a repeat of the recent past. That's a decent enough question. Climate skeptics will point to two periods of warmth, what's called the Eemian, E-E-M-I-A-N, and the medieval climate anomaly. Okay, so now the medieval climate anomaly happened about 1,000 years ago. This is roughly when Scandinavians, the Vikings, settled what we called Iceland and Greenland. Okay, because it was much warmer then. It is not particularly well documented outside of the North Atlantic, so it's hard to tell if this was a global event or if it was simply a local or regional event. Okay. The medieval climate anomaly, likely not a global event, but notice likely, but you cannot really say with certainty. So these are more than likely, and this is more than likely an event that happened on a local scale to the North Atlantic. Tree ring data basically talks about the fact that this medieval climate period was about 0.7 of a degree cooler than it is today. A little bit of an ice age post that point. And the reason warmth, meaning the last 20 plus years, it's really the warmest it's been in about a millennium. So you can begin to sort of associate what's happening now to what happened during this medieval climate anomaly. The other one would be the Eemian-interglacial. And again, interglacial meaning between glacial periods. It roughly happened between 75 and 130,000 years ago, and it peaked around 125,000 years ago, warmer than today, and sea level was about 5.5 to 9 meters taller. It was broken down into 5 major phases, 3 interstadials, warming, and 2 stadials, cooling. And this graphic coming up here will sort of highlight the different events. So the last interglacial, also called the marine isotope stage 5, I know, crazy name for it, but basically it's based on oxygen isotopes from marine sediment cores. And there are 5 phases, A through E. A, C, and E were warming ones, and 5, B, and D were cooling events. Okay? And here it is. This is 200,000 years ago, 150, 125, 100, and 75. And these events happened between 75 and about 130,000 years ago. So this is 5E, 5C, and 5A were the warming bumps, and 5B and 5D were the cooling events. Okay? Notice, this is where we are today. And this is when we came out of the last ice age at about 11,700 years or so ago. We began to warm to where we basically are right now at year 0. Year 0 would be now, today, okay? But the Eemian is most like today. Notice this period here, if you take it, it's roughly like it is today, even though it's slightly cooler. And so basically the Eemian is a good analog, meaning comparison, for the most recent period now, okay? And evidence from ice cores and deep sediments indicate that it was warmer, that it lasted about 12,000 years. That's lower ice volume than we currently have. So there was less ice in Greenland and Antarctica, and sea level was higher than it is today. And there are 2 estimates between 4 to 6 meters. And here's a great image of coral that is now above sea level. But you know, coral has to be roughly 6 to 8 meters below the surface. So what does this tell you? That the water level must have been higher in order for this coral, which is now dead and fossilized, to basically have been alive. So this gives you a sense of, this is a little bit of evidence of telling you where the sea level used to be. Okay? So that's where I'll leave it today. Again, please make sure that you watch the first part of the video. So that's basically in the week 9 folder. First half of that video is IPCC. The second half is the first part of the Paleoclimate. This is the second part. And there are also some nice videos that are linked on the week 9 folder dealing with oxygen isotopes. So the 16 oxygen and 18 oxygen discussion that was had in that video presentation. I hope you're doing well. And if you have any questions, please let me know as soon as you can. Hope you're doing well. Talk to you soon. Bye.